Hello students, I am Dr.Prabir Panja, Assistant Professor, Department of Applied Science, Haldia Institute of Technology. Today we will discuss about the basic idea about linear transform and some of its properties. So, linear transformation. So, linear transformation, especially a mapping. So let V and W be two subspaces over the real field F. Then T is a mapping from V to W is called linear transformation. If it satisfies some properties. Property number 1, T of alpha plus beta equal to T alpha plus T beta. Okay, for all alpha beta belongs to V set. Okay, and another condition is T of C alpha that must be equal to C into T alpha. Okay, and here C is a constant and C belongs to the field set F. Okay, so if a mapping T from a vector space V to another vector space W satisfies these two property, T of alpha plus beta equal to T alpha plus T beta, and another is T of C alpha is C into T alpha, then we can call this mapping T as a linear transform. Now we'll check a particular mapping will form a linear transformation or not. Suppose we have a particular problem. Problem number 1. So let T is a mapping from R3 space to R2 space is a mapping defined by T of xyz equal to 3x minus 2y plus z, comma x minus 3y minus 2z. The question is check T is a linear transformation or not. So this is the question. Now we'll try to verify this will be a linear transform or not. So what we'll do first we'll take two elements from the domain set R3. Let alpha equal to x1, x2, x3 and beta is y1, y2, y3. These two are from R3 set. Okay, now T of alpha is T of x1, x2, x3. So the value will be equal to, from our mapping, it will be 3x1 minus 2x2 plus x3 comma x1 minus 3x2 minus 2x3. Okay, so this is the value of T alpha. Now T beta, so the value of T beta will be equal to 3y1 minus 2y2 plus y3 comma y1 minus 3y2 minus 2y3. Okay, so this is the value of T alpha and T beta. Now we'll compute alpha plus beta. Alpha plus beta is actually equal to x1 plus y1, x2 plus y2, x3 plus y3. Now if we compute T of alpha plus beta, so that will be equal to what? That will be the value 3 into x1 plus y1 minus 2 into x2 plus y2 plus x3 plus y3 comma x1 plus y1 minus 3 into x2 plus y2 minus 2 into x3 plus y3. So this is the value of T of alpha plus beta. Now we want to arrange this whole expression. Now it will be 3x1 minus 2x2 plus x3 plus 3y1 minus 2y2 plus y3 comma. Now if we arrange the second term, it will be x1 minus 3x2 minus 2x3 plus y1 minus 3y2 minus 2. Now again, if we rearrange the whole expression, so that will be equal to 3 into x1 minus 2 into x2 plus x3 comma it will be y1 sorry, this will be okay, y1 minus 3y2 minus 2y3 plus 3x2 sorry if we come here, this will be now if we come again here, so okay, so it will be then x1 x1 minus 3x2 minus 2x3 plus 3y1 minus 2y2 plus y3 comma y1 minus 3y2 minus 2y3. Now if we carefully observe the whole expression, this and this will be nothing but T alpha. This is the expression of T alpha plus T beta. So the first condition for a linear transformation is already hold. Now we will check the second condition, T of C alpha. T of C alpha. Now this will be equal to T of C alpha means Cx1, Cx2, Cx3. Okay, since alpha is already considered as x1, x2, x3, three-dimensional point. Now if we put this value in our mapping, it will be 3 Cx1 minus 2Cy1, sorry, 2Cx2 plus Cx3 comma Cx1 minus Cx2 3Cx2 minus 2Cx3. Okay, now if we simplify the term, it will be what? C into it will be 3x1 minus 2x2 plus x3 comma x1 minus 3x2 minus 2x. Okay, so now if you check this whole, it is nothing but C into T alpha. So both the conditions holds for this mapping T. So we can say that the mapping T is a linear transformation. Okay, so in this way we can check any particular mapping will be a linear transformation or not. Okay, now we'll go for another type of linear transformation, that is called identity transformation. Now what is this identity transformation? So let V be a vector space. Okay, let us consider V is a vector space. Now if we define a mapping, let I be a mapping from V to V. Okay, so let us define a mapping I from V to V. Now if I of alpha become alpha for all alpha belongs to V, then we can say that the transformation I is a identity transformation. Now another transformation is zero transformation. Now what is this zero transformation? Zero transformation is another type of transformation. So let us consider, let V and W be two vector spaces. Two vector spaces. Vector spaces. Okay. So let us consider these two vector spaces V and W. Let theta and theta dash be the null vector. Be the null vector in V and W respectively. Okay. So we are considering here two vector spaces V and W, and corresponding null vectors are theta and theta dash in V and W respectively. Now, if we define a mapping O from V to W, and if this happens that O of any alpha is theta dash. Okay, so V and W are two vector spaces now, and theta dash are the two null vectors in V set and W set respectively. Then if we define a mapping O from V to W such that O of alpha become null, that is theta dash, then O is called zero transformation. Okay, so this is called zero transformation. So if we draw the set, so this is V and this is W. Okay, and this is the mapping O from V to W. If we take any alpha from here, and if its image become always null, theta dash, then the corresponding mapping will be called the zero transformation. Okay, now we'll try to establish some result on the identity transformation and zero transformation. So theorem number 1. Let T V to W be a linear transformation. Okay, then we can establish here two results. Result number 1, T of theta, that will be equal to theta dash. This is the result number 1, where theta and theta dash are the null vectors in V and W vector space respectively. And another result we can establish, that is T of minus alpha, that is equal to minus of T alpha. Okay. So we will establish here these two results. Now, so we know that theta and theta dash both are the null vectors in V and W respectively. So we can write here that theta plus theta is equal to theta. Okay, because the addition of two null vector is again a null vector. Now, if we apply transformation T over both sides, so that will be T theta. Now, theta plus theta is again, we can write theta. And since T is a linear transformation, so we can write it as T theta plus T theta. since we know that T of alpha plus beta is T alpha plus T beta, since T is a linear transformation. T is a linear transformation. Now, if we add minus T theta in both sides, what will happen? So T of theta minus T of theta. So that will be T theta plus T theta, okay, minus of T theta. Now T theta minus T theta. So it will be what? Theta dash, since T theta is from W set. Now it will be equal to T theta plus, we can write it as T theta minus T theta. Okay, so theta dash is equal to T theta plus theta dash. Now again we can simplify this result, that theta dash value will be equal to T of theta, since theta and theta dash are the null vectors in V and W respectively. So result number 1 already proved. Now we want to prove our second result. Okay, so we know that T of alpha plus T of minus alpha, that is equal to what? Since T is a linear transformation, we can write as T alpha plus T of minus alpha. Okay, now left hand side we can write alpha plus minus alpha as theta. Okay, since minus alpha is the additive inverse of alpha, so if we add alpha and minus alpha, it will gives you theta. Now T of theta, it will be T alpha, and since T is a linear transform, so we can write, okay, so plus T of minus alpha. Now in the proof number 1 we already get that T of theta is theta dash. It is coming from proof number 1. So theta dash value is equal to T alpha plus T of minus alpha. Now from this result we can easily say, say that T of minus alpha is minus of T alpha. So the proof 1 and 2 is completed. Now we will go for another important result, that is kernel of a linear transformation. Kernel of a linear transformation. So let us define a linear transformation first. So let T V to W be a linear transformation, and let also theta and theta dash be the null vectors in V and W set respectively. Okay, then kernel of T is the set. Okay, then kernel of the linear transformation T is defined this way. Kernel of T is the collection of those alpha. That alpha must be belongs to the domain set V, and that satisfied the condition T of alpha equal to theta dash. Okay, so kernel of a linear transformation is a set. It is the collection of those alpha whose images become null. Okay, so this is the concept of kernel of a linear transformation. Now we want to establish another important result of linear transformation, that is for a linear transformation T, for a linear transformation T from V to W, for a linear transformation T from V to W, kernel T is a subspace of V. Okay, so this is very important result you want to establish. So first what we have to do, a linear transformation T is given here from a vector space V to another vector space W, and we want to prove kernel T is a subspace of V. Now kernel T is a set, collection of some vector alpha, and that alpha must satisfy this condition. Okay, so obviously we can say that what kernel T, that will be subset of V. Okay, since kernel T is the collection of some vectors and V is the collection of large number of vectors. Now we want to establish that kernel T is subspace. So let alpha beta be two vector from kernel T set. Okay, so if alpha and beta two vectors from kernel T set, that will satisfy the condition of kernel T set. So that is T of alpha will be theta dash, and similarly we can write T of beta, that will also be theta dash. Okay. Okay, so now T of alpha plus beta, T of alpha plus beta, since T is a linear transformation, so it must satisfy this condition T alpha and T beta, and we already get that T alpha theta dash and T beta theta dash, and theta dash are nothing but null. So null, addition of two null vectors is also a null vector. So T of alpha plus beta is theta dash. So we can say that alpha plus beta vector must be in kernel T set. Okay, so this is the first condition for a subspace. Now we will check the second condition. So T of C alpha. Since T is a linear transformation, so we can easily write T C alpha as C into T alpha. Again, we know that T alpha is theta dash. So C into theta dash. Now if we multiply any real number with null vector, then it will give us again the null vector. So ultimately we can say that this C alpha is also from kernel T set. So both the property for a subspace hold, then we can say that kernel T is a subspace of V. Okay, so in this way we can establish many important results, and some other result will be discussed in the next class.